Hello everyone, welcome back to Math Hands-On with Python class, and today we are going to have a lecture session on the crashing of a project. So we are still with the main topic of project management. So now let's see how we can crash the duration or time scheduled for our projects. Okay, so what does it mean by crashing of a project? So the process of shortening the time to complete a project is called crashing, and is usually achieved by putting into services additional labor or machine to one activity or more activities. So it shortens the project duration by reducing one or more critical activities to a time less than the normal activity time. So crashing project normally involves more cost. So project crashing seeks to minimize the extra cost for completion of a project before the stipulated time. Now let's see the time cost relationship. So we have seen that crashing projects involve more cost. So let's see the relationship existing between time and cost. So it is assumed that there is a linear relationship between time and cost. And this graph here demonstrates how the cost and time are linearly related. So you can see we have demonstrated 2 points here, and one node or 1 point comprise of the normal time and the normal cost. So decreasing the time, you see the line connecting these 2 points is increasing. Okay, so that means whenever you decrease the time, so the cost is increasing. So reaching this point, if you are decreasing the time from this normal time at a certain point here, let's call this is the last point. This point we call it a crash time or crash duration, and its corresponding cost is called crash cost. Okay, so the slope of this line connecting these 2 points is what we call the cost slope, and this cost slope is mathematically calculated as the ratio of the difference between the crash cost and the normal cost to difference between normal duration and the crash duration. Okay, so now let's use this example to illustrate how we can perform crashing of a project. So consider the given project data in a table. Crash the project duration from its original duration to a final duration of 110 days, assuming the daily indirect cost of 100. So you can see these are the information that we are having in our table. We have activity predecessor, normal duration and normal cost, and also we are having information for crash duration and crash cost. Okay, step 1. When you are performing crashing of a project, the first step is to construct a network diagram. So the respective network diagram for the given information it looks like this one. So we have activity A up to E, but we start with the dummy activity and we are going to end with the dummy activity. And these activities, we have the corresponding duration. Okay, so dummy activities, basically they don't consume resource or time. So we have 0 duration and the 0 duration here. So we have managed to draw a network diagram, and now let's fill the informations required in this network diagram. So in the previous video we have shown on how we can find the earliest start information and the earliest finish together with the latest finish and the latest start. So we are not going in details in that because we have did it in a previous video. So let's fill the informations required in this network. Okay, so we have the informations for earliest time and the latest time. So after this now, we have to determine the critical path. The critical path basically is formed by those activities with 0 total float. So we can see that activity B, activity C, activity D, activity E have 0 total float. So this form critical path. So we have a critical path in these activities. So we have critical activities B, C, and D. And now after having these critical activities, let's now go to the next step, which is the computation of the cost slope for each activity. So let's consider the table that we were having previously. Now we add two columns, one for the cost slope and the other for the ranking of the cost slope. So the cost slope, as I said, is the ratio of the difference between the crash cost and the normal cost to the difference between the normal time and the crash time. So we have the crash cost here and we have the normal cost. This is the crash duration and this is the normal duration. So performing this mathematics here, you're going to end up with this column. So after this one, now we have identified that B, C, D, and E are critical activities. So we are going to rank these critical activities because crashing is going to take place in these critical activities. Basically, from previous video, we have seen that non-critical activities, the total float is non-zero. That means you can delay for some times in those activities, but you cannot affect basically the total final projects. But any delay in the critical activities will affect the total project duration. So that means if we reduce the number of days in these activities, then it will be in a position to reduce our total project duration. Now, ranking from the lowest cost slope of the critical activities, we are going to have this ranking here. Okay, so the lowest cost slope for a critical activity D is 60, and followed by the activity E, and then activity B, and the activity C. So after having this cost slope and their rank, now we go to the next step where we are going now to select lowest ranked critical activity and we start crashing the projects. Remember, we have this network here, and I have added the other information like you can see. Let's consider this part of the main table. We have activity, normal duration, and cost duration. So this information here, 20 for activity A, represent the number of crashing days that are allowed in this activity A. That the difference between normal day and the crash day is the maximum number that are allowed to crash for activity A. Also for activity B, you can see the difference is 5. You can see here we have maximum number to crash in activity B is 5. And this other number are penalties. For each day that you are going to reduce in an activity will cost you this amount here. So let's now perform the crash process, okay? But we are required to perform crashing for a current number of days that we are having for our project, which is 140, okay, to 110, okay? So now, to do that, we are going to start crashing for critical activities with a smallest ranking or a smallest cost slope. So activity D has a smallest cost slope, and they have a maximum number of crashing, which is crashing days, which is 10. And then remember, we need to reach 110, and we have 140. That means we can take this all 10 and reduce this number here. So crashing this activity, then it will affect its duration for this completion, and it will affect also earliest finish, and it will affect the next activity, the last one, this one also for activity A. Now, if so, after crashing, you need to recompute these informations so that they can reflect the changes. Now, recomputing that, we are going to have this new network, okay? So we have this new network. We are done with this one. That's why you can't see the information for the maximum number of crash days and the associated cost slope, because we have exhausted all days allowed to crash for this activity. Now, you can see we have reduced the project duration from 140 to 130. And now, let's recompute and check if this critical path is still critical, or if there is an addition of a critical path. So we can add the normal duration for the different activities in different paths. Like the first one, we were having 20, this is 60, 80, and this makes 130, okay? So this still have 130 as the final one. And let's go to second root. We have 20, 80, and then 50. We have 130. That means these two paths have the same completion day. And going this way, this one is not a critical path because the float here is not 0. So, but checking for activity F, its float is 0 and here is 0. That means we have developed a new critical path, which is this one. So now we are going to have two critical paths, and we still need 20 more days to crash from the total project duration. Now, to do so, we have to go through these critical activities and check for the activities with the lowest cost slope. Okay, so you can see this one, we have 600, 300, 200, 120, and then this one have a lowest cost slope. Okay, and apart from lowest cost slope, remember we have two critical paths. If we reduce any number of days from this one, it will not affect either of the critical path, because both of this critical path, they share this point. So if this one could be here, it will be difficult to reduce or to crash the days at one activities only, because we are not allowed to change the critical path into non-critical path. So the critical path should remain critical path. So since this lowest cost slope is at activity E, and we can reduce this without affecting any of our critical path, then we can reduce these days, or the total completion days, by this amount of 10 days. Okay, so we are going to take those 10 days, and again you need to recompute, because it is going to affect the duration of this activity, because we have reduced it to 10 from this normal. Now it is going to be 40. It is going to affect the earliest finish time and the other informations in the other activities. So recomputing it, we are going to end up with this. So this table here have a completion day of 120. Okay, so you can see that we didn't distort our critical paths. So our critical paths are still critical. And now let's check for the other activity. So this activity A now have become a critical activity, and they also have formed a new critical path, because we have a path through this activity A. So we can see now we have a new critical path which is from start A to end. Now at this point now, still we need 10 more days to crash from these critical activities, and all activities now here have become critical. And how are we going to reduce those 10 days? If we can reduce the 10 days, looking for the minimum cost slope, we have 300, 200, 600, 100. So the minimum cost slope for critical activities is 100. So taking 10 days here will affect this critical path, because this will reduce this one, and the number of project completion here will go to 110, will become non-critical activities. So it's not allowed for critical to be non-critical activity. So we need to do something such that this critical path should remain critical, and the critical activity should remain critical activity. So we need to see how we can perform this crashing of days from multiple activities. So let's consider if we can crash here. Okay, the other point which we can crash associated with the middle activities of this two critical path is activity B. That is, crashing the same number of days from activity A and B will not affect our critical path. That means from this two activity A and B, the minimum number of days that can be crashed for these two activity without changing the critical path is 5 from activity B. That means if I take 5 from activity B and 5 from activity A, so the critical path will remain critical. So doing so, we are going to change the critical or number of days that we can crash from activity A to 15, and this number of days at activity B will be all being reduced. So from there, we need to recompute the informations in our activities. You can see we have reduced 5 days here, we have reduced 5 days. So you need to recompute these informations in your table to reflect the changes. So doing so, we are going to have this network here with some reflection changes. Now, after recomputation, we have seen that we have reduced the number of days of a project from 120 to 115. Okay, and still our critical paths are critical, and we need more 5 days to reduce from these critical paths. Okay, so here we have already used all of them, and you can see we don't have a shared point to reduce from these two critical paths, so we can't reduce number of days from A only or A and C, because will affect the other route. So what we do, we have to reduce those 5 days from activity A, C, and D, F, because are the only ones that we are having. So we are going to reduce 5 days so that we can attain this optimal number of days that we are required to achieve. So we are going to reduce 5 days from A, C, and F. So from A, we are going to remain with 10 days, here 5 days, and here we are going to remain with 10 days. Okay? Now, after reducing those 5 days, we need to recompute the informations into our activities, and then we are going to end up with this new network. So we have managed to crash the project from the 140 days to 110 days. And this is the final network, which shows the total number of duration for each activity. Okay, so we have managed to do so, and now after this one, we needed to compute its associated cost after crashing this project. So its associated cost, basically, we have this summary table here on how we can compute the associated cost for project crash durations. So the associated costs now are computed for each activity and then added to the normal or direct cost. So this direct cost, this 48,300, normally is the sum of all normal costs. Okay, so adding all normal costs from the previous table or from the original table, you'll have this direct cost for the project, which basically is for 140 days. And we have indirect cost. In the question, we were told that the daily indirect cost is 100. So every day, when you are performing the operations, there is indirect cost which is 100. So for original project, before starting crashing, so we have to take 140 days multiply with this indirect cost for every day of the operation for 140 days. So we have this indirect cost for the 140 days of, or for the normal project duration, which is 140. And we have to add the cost of our project now, the direct one and the direct, and the total project cost before crashing, it was 62,300. Now let's see what will be the cost after crashing. We have seen that activity A have been crashed by 10 days, activity B by 5 days, C by 5 days, D by 10 days, E by 10 days, and F by 5 days. So we end up with 110 days. Now, to obtain the associated cost after project crashing, we take the direct cost or the original cost before starting crashing, then we add the cost associated by crashing each day from each activity. Starting from activity A, we have seen there are 10 days, but every crashed day, it will cost the amount which is equivalent to the cost slope. So taking 10, you are going to take 10 days crashed, multiplied to its associated cost slope. Okay, you will have the cost increase for our project by crashing number of days for activity A. And we go also we add with the cost associated with the crashing number of days for activity B. So activity B, we crashed the 5 days and its associated cost slope is 200, plus activity C, we crashed the 5 days. We multiply by its associated cost slope, which is 600, plus activity D, we crashed the 10 days, times associated cost slope, which is 60, plus cost for activity E, which is we crashed the for activity E. For activity E, which we crashed the 10 days, multiplied with its corresponding cost slope, which is 120, plus 5 days, which we crashed it from activity F, times its corresponding cost slope. Then we have a total of direct costs after crashing the project to 110 days, which is 56,600. So its corresponding indirect cost is now the number of or duration of the project after crashing times the indirect cost for daily operations, which is 100, and now we have the indirect cost as 11,000. So adding indirect cost and the direct cost, we are going to have the total project cost after crashing, which is 67,600. So this is how you can perform crashing of a project and computing its associated cost. So thank you for watching. Don't forget to subscribe, comment, like, and share this content of this video. If you have any question, please just write into the comment section and I will go through the question or your comment. Thank you and goodbye.